Good morning and welcome to this presentation with the title Implementation of a Vision-Based Worker Assistance System in Assembly. In this work, we will show you how to implement worker assistance systems in cyber-physical production systems based on an industrial case study. First, let's introduce what is a cyber-physical production system. So the single elements of cyber-physical production systems are our cyber-physical systems. This could be our digital workplace, a transfer system, a feeding system for screws or else, a robotic system or automated system, as well as also worker assistance systems that help the operator to complete his tasks. So all these single intelligent elements, or CPS, enable the communication between the human operator, the machines, and the products in our production system. So therefore, cyber-physical systems are able to acquire and to process our data that we retrieve in production, to guarantee also certain self-organization and self-control of certain tasks, as well as also the interaction with humans through digital interfaces. So in our work, we want to focus on worker assistance systems in such cyber-physical production systems. We have seen that in scientific as well as also managerial literature, there's a certain lack also in applications of worker assistance systems in cyber-physical production systems. Therefore, we want to validate our model that we developed based on an industrial case study. So regarding worker assistance systems, they usually help us to acquire data at the operator workplace. They help us also for scene understanding, to understand better what's the environment of our operator. They help us to process data, to structure the data that we can gather, to analyze the data through data analytics tools, also to conduct simulations and to use and interpret this data for having a certain synthesis, and to use this data also for digital twin-based control, visualization of the data to our operator, as well as allowing also our system or our human operator to interact with the technical system. First, before we begin to explain our developed model, brief review also on the categorization of worker assistance systems. So basically we have three categories. These three categories are sensorial assistance systems, physical assistance systems, and cognitive assistance systems. So sensorial ones are those that are giving us a certain optical signal or auditive signal. In this example, you see this earring device, which gives a light signal to the operator in order that he knows where the robot is moving. Then for the physical assistance systems, this could be a robot that is reducing the physical workload of the operator, or also an exoskeleton like we see it in the picture. And then we have cognitive assistance systems that are using data, they are processing data, and they are visualizing or giving us information in a certain way that we are supported in decision making. So to present the case study that we will talk about in the next slide, it's a product from an industrial company. We work together. It's a high voltage power bar for electric vehicles. And the process for such a project is bending of the material, lasering, welding, quality control, assembly, and end-of-line test. So the objective of this case study will be how to integrate or to realize a vision-based worker assistance system for such assembly workstations based on a model that we will show us on the next slide. So the generalized model for such a vision-based worker assistance system integrated in a CPPS environment is the following, and is structured in 5 modules. The first module is data acquisition, so we gather the data. In module 2, we have data pre-processing, structuring the data and going from raw data to valuable data. Module 3 is like the core of this model, being the database, the data storage place. And then this data is used in Module 4 for data analytics, as well as also in Module 5 for simulation purposes, and then used for sending back the results, for example, of simulation to the production planning software, and therefore optimizing the workflow at the assembly station. So taking a look to the single steps of this model, we see here Module 1, data acquisition. Here the data of the operator's activities is captured in our case study by a sensing device. We used here Orbic 3D Astra S camera positioned on the top of the workstation, focusing also with the depth camera on the table of the workstation. The SDK of Orbic allowed us also the communication between the sensor and the computer, and OpenNI2 gives us the opportunity to gather data by Python and for doing the pre-processing in the next step. So the next step is then Module 2, data processing, pre-processing. So we convert the raw data from the workstation into meaningful data. Here in this example, our raw data consists of a set of points in the 3D operator workspace. We developed an algorithm in Python to detect hand movements and movements of the operator and to interpret this data as specific assembly activities. This data is structured in a SQL database, and we have a communication between Python and our SQL database. So Module 3 shows us now the core of the work with the SQL database, where all the systems are sending the data as well as also retrieving the data for further analysis. This SQL database is communicating in our industrial case study with software systems that are first Visual Shop Floor for visualization and shop floor management, RStudio for data analytics, as well as FlexSim as a discrete event simulator for doing simulations for production optimization. All this integrates information of our system or production system, and therefore basically it fulfills the service of function of a manufacturing service bus. In Module 4, we have data analytics using multiple linear regression for predictive analysis, as well as data mining for analyzing historical data. RStudio is used to extract the data from the database and to do analytics based on the data in real time. We can visualize through our visual shop floor system histograms, control charts, or different charts for informing production leaders or shift leaders or the operators. And alerts can be created to inform users or production managers in real time by using mobile devices like the smartphone. The fifth module is simulation. Here we retrieve the data from our manufacturing execution system in production, taking the initial production plan, sending it to the SQL database, performing based on that and the information from our workplace, from our vision-based worker assistant systems, simulation that is automatically performed, and using the results of this simulation to optimize our production plan and to send back this information afterwards to the production planning software or the MES software. Some details on the architecture of the module based on this industrial case study. So we started at the beginning from a very generalized model for integrating such worker assistance systems in CPPS. Now we see that in our industrial case study, we have different systems or software systems and communication protocols that are becoming important. For example, in data acquisition, we work with our sensing device from Orbeck. In data pre-processing, we use mainly Python. Data storage is our SQL database. Data analytics is based on our Studio as a software. Visualization is done by using Visual Shop Floor software. And in simulation, we are using FlexSim as simulation software. And in production planning, we connected our system with the MES system, which in this case was process. Now to conclude the work, we want to show what has been the outcome. So the model worked as expected, and the company is already expanding this model or this realization also to other production lines in their company, as well as also to other production sites at the company. We have seen that the model helped a lot in the implementation phase because it gives you a certain guideline through the design stage. We have also seen that the use distribution models and the data has been suitable for modeling and simulation purposes. Python and RStudio, as well as the SQL database, have run simultaneously, and we didn't have any further or larger problems or interruptions. And the user can now receive a lot of valuable and useful notifications to the smartphone or other mobile devices through pushover. So in total, we have a lot of advantages through the use of such a vision-based worker assistance system. So I hope that I could give you an introduction in how to implement such vision-based worker assistance systems in production, and thank you for your attention.